Hello, Algebra 2 geometry students. This is our complex rational expressions video. So a complex rational expression, or a complex fraction, is what it's often called, is just like when you have a fraction, but either the numerator or the denominator is also a fraction, or both, I guess. So there's two ways to simplify these. When I say simplify, I mean get it so that there's not a fraction inside a fraction anymore. Like somehow get rid of these fractions so that we just have a regular fraction without a fraction inside the fraction. I've said that word a lot now. So there are two kind of methods for doing this. Method one, I'll show you, but I kind of always use method two, but we'll talk about this one first. So one thing you can do is you can add the two fractions in the numerator and the two fractions in the denominator together, and then you divide by flipping the bottom and multiplying. So what that would look like here is you would add these two. Your common denominator up here is going to be 4. To get this one, the denominator of 4, I got to multiply by 2. This one already has that denominator, so this is 2 plus 3 over 4 on top. And on the bottom, I would add these. The common denominator would be 24. So times 4 to get there from the 6 makes it 20 on top, and times 3 gives me a 9 on the top here. So this is really 5 over 4 on top and 11 over 24 on the bottom. So all I've done so far is add. That's the adding part of this method. And then I divide by, hopefully you all know how to divide fractions. You multiply by the reciprocal of the one on the bottom. So 5 over 24, 5 over 4 times 24 over 11. We can do a little simplifying here. That's a 1 and a 6 there. So I get 30 over 11. So that's one way to add these together, or one way to simplify these is to add the two fractions on top, add the two fractions on the bottom, and then divide those fractions by each other. And you can see now that this fraction that's here at the end is no longer what I would call a complex fraction. It's just a regular fraction with just one thing in the top and one thing in the bottom. That's method one. It's like, it works okay when the fractions are like just numbers and not variables, but when they become variables, it gets more tricky. So I like this way better. And this is what it says, multiplying by the LCD. So when I say this for this, I mean the LCD of all denominators in the fraction. You may remember that if I have a fraction, I can multiply the top and bottom by the same thing, and it doesn't change the value of the fraction. So that's what I'm going to do here. I'm going to multiply the top and bottom by a number, which is going to be the denominator, the LCD of all the denominators in the fraction. And what's going to happen is all the fractions are going to go away, and I'm just going to be able to just add and subtract the things that are left. So to find the LCD of all the denominators in this fraction, I know I have a 2, that's this one. I have 4, which is 2 times 2. I have 6, which is 2 times 3, and I have 8, which is 2 times 2 times 2. So these are all my denominators here. These are all I would call those the prime factorizations. I've like determined what every factor of each denominator is, and I'm going to build my LCD. We did this already once. So I start with this one. You can honestly start with the biggest one because you're always going to need all the factors of even the biggest one. So I'm going to start with 8. I'm going to do 2 times 2 times 2. Now I check, if I want 6 to be a part of this LCD, I got to make sure that all the factors of 6 are in here. 2 is the first factor of 6, and there's already a 2 in there, so I don't need to add that one. 3 is the second factor of 6. It is not in my denominator yet, so I must add it. So I've taken care of 8, I've taken care of 6. 4 is 2 times 2. I can see that I already have a 2 times 2 in this one, so I'm done with that. And 2 is just 1, 2, and I already have 3 of those. So my least common denominator of all these fractions is 24. So this is what I'm going to multiply the top and bottom of my original complex fraction by. So what that would look like is, I'll draw this one again. I'm not going to write it again because I have special and I have magical powers. So I'm going to do times 24 on the top and times 24 on the bottom. And I can do that. 24 over 24 is just like the number 1. So I can multiply a fraction by 24 over 24 and not change its value, because multiplying anything by 1 does not change its value. So let's see what happens. Remember, I got to distribute this to everything on the top and the bottom. So I wouldn't normally write out every one of these steps, but I'm going to this first time so we can kind of see what's happening. 24 times a half plus 24 times 3/4 over 24 times 5/6 minus 24 times 3/8. And this gives me now 24. If you can think of a fraction as like you multiply by the top and divide by the bottom. And that's going to be a good thing to do here. We're going to divide by the bottom first, then multiply by the top. So 24 divided by 2 is 12. 12 times 1 is 12. For the second multiplication, I do 24 divided by 4, which is 6. And then 6 times 3 is 18. Do the same thing on the bottom. 24 divided by 6 is 4. And 4 times 5 is 20. And then for the last one, it's a minus this time. I do 24 divided by 8, which is 3. 3 times 3 is 9. Now if I add the two numbers on top, I get 30 on top. And I subtract 20 by 9, I get 11 on the bottom. And that checks out with my original. Like these ought to give you the same answer, and they do, these two methods. But like I said, I prefer this one personally. I like the idea that you can just get, like, you see we had 4 fractions inside my fraction, and then I multiplied by the LCD, and now I have no fractions, just numbers, 12 and 18 and 29. So that makes that a lot easier. So maybe the hard part there is getting the LCD and then doing the multiplication. But I think getting used to the idea that multiplying by a fraction is like dividing by the bottom and then multiplying by the top makes this much, much easier. And it's like, those tend to be very small operations when you do them. So you will not be surprised to hear that we will not be doing this with just numbers for the most part, if ever again. We're going to be doing it with expressions like this, where the denominators aren't numbers. They're like, they have X's and Y's and A's and B's and all kinds of stuff. But the reason I did this example here is because the method that we use for these two is the same as the method that we use for this one. So here's what it is. You find, depending on how you want to do it, I'm going to use this method where I find the LCD and multiply by it. If you want to do it this way, have at it. I think it's easier to do it the second way. So to do this, we find the LCD of all the fractions. We look at, there's 4 fractions in here. I got to find the least common denominator for a cubed b, for a squared, b squared, and for b squared. So I'm going to write those over here. Oh, I'm writing it in red today. That's fun. A squared, b squared, and b squared. And I'm going to build my LCD from these. There's like not really much factoring that can be done at this point. They're kind of already factored. You just kind of have to recognize that this first term has 3 A's and 1 B in it. So I'm going to start with that. LCD a cubed b, that's the first one. Done with that. This one is just b, and I already have a b, so I don't have to worry about that. This guy has 2 A's and 2 B's, so I have 3 A's, so I don't have to worry about that. But I only have 1 B so far, so I got to add 1 for this b squared. So 2 A's, already got 3. I can ignore this. This had 2 B's, but my original thing only had 1, so I had to add 1 B. And this one is b squared, so 2 B's, and I already have 2 B's. So this is my LCD right here. And again, I feel like this method is what we did here with the 2's and the 3's is the same as what I did here. This time I'm just using A's and B's and stuff. Okay, so now my plan is to multiply my original fraction by this LCD here. So times a cubed b squared times a cubed b squared. And this is where the dividing and then multiplying thing comes in real handy. So I'm going to write out all four terms with the multiplication, the distribution, but I don't necessarily think you should do that every time. Once you get a little more comfortable with this, you won't be writing every one of these steps maybe, but I'm going to do it. Remember, I'm distributing this thing to both of these fractions. I'm distributing this thing to both of these fractions. So I got a cubed b squared times 1 over a cubed b That's this times this. Then we got a cubed b squared times 1 over b all over a cubed b squared times 1 over a squared b squared minus a cubed b squared times 1 over b squared. So I just multiplied this thing, this LCD, times every term in the top and times every term in the bottom. And this kind of looks like a mess, but I promise it's going to get a lot easier. It's going to get a lot simpler, this expression. So this is why I think you should think about division first. So if I do a cubed divided by a cubed, I get just 1. These like kind of cancel each other out. And now there's no a cubes left. This b squared cancels out with that b, leaving just 1b on top. And then times 1 is just b. So let me do that one more time because it's maybe important to get it right the first time. So I did a cubed divided by a cubed and I got 1. I did b squared divided by b and I got b. Then I multiplied that by the numerator, which in this case is just 1. I just got b. This whole thing just turns into b. You notice this was a fraction before and now it's not, and that's the whole point of doing this. I can't divide this one. The only thing in the denominator is b. So the a cubes have to stay. The b, the 3 a's here have to stay. The b squared divided by b, it just gives me 1b again. So I have a cubed times b times 1. That's a cubed b. You kind of think of it like this. Cross out the 2 and cross off that. All the a cubes have to stay. A cubed b times 1. This one, a lot of stuff is going to go away. Let's see. I have b squared and b squared. And then I have a squared and a cubed turns into just an a on top. And I got a times 1, which is just a. Now in minus, let's see, the a cubes have to stay because there's no a's in the bottom. But both the b's in here and both the b's down there will eliminate each other. And I'm left with a cubed times 1. So it's a minus a cubed. Yeah, nothing else I can really do here to simplify this. It's no longer a complex fraction, so in that sense, it's been simplified, but yeah, you could factor the bottom and the top a little bit, but some things might happen. Yeah, I'll do that. So this one's a little more complicated because once you do this, if you factor the top and bottom, I think there's stuff that can cross out. So you do b times 1 plus a cubed on top and a times 1 minus a squared on the bottom. This is a sum of cubes, which we learned first semester or some point, maybe it was this semester, that can be factored. SOAP, right? This one plus that one times the first one squared, opposite, and then plus the second one squared. And the bottom is, this is a difference of squares. So it's 1 minus a times 1 plus a. Now these 1 plus a's can cancel out. Now you have to stop, but I guess my point here, this is like the point of today's lesson really is, do you know how to get to here? Okay. This one, you really, if it says simplify completely, the question, you're going to have to get down to here eventually. You have to figure out how to do that. So we can talk more about that in class if you want to. If you're like, I don't understand how you got from this step to that step, that's fine. Happy to talk to you guys about it. But just know that the whole point of this is find the LCD of all the fractions in the complex fraction, and then multiply everything by it. You can see that all the denominators end up canceling out, which is the point of this. End up with just things added on top and things subtracted on the bottom. So do a couple more examples in the next video. But that's pretty much the lesson for today.